My name is Genevieve Langdon, and I'm here to talk to you today about improvements to V-hull structural design for air blast loading applications. I'm a Professor of Blast and Impact Engineering in the Civil and Structural Engineering Department at the University of Sheffield. I'd like to take a moment to acknowledge my co-authors at the University of Cape Town, who were vital in being able to perform the experimental work. First used by South Africa and Rhodesia, the V-hull has become a global feature. It is used because it's very effective at directing the explosive blast wave laterally away from the crew, rather than vertically upwards. As a design, it has saved many lives and reduced casualties from anti-vehicle landmines significantly. On the right-hand side of your screen is a photograph of a Cougar mine-resistant ambush-protected vehicle that hit a landmine buried in a hole filled with water. On the left-hand side of your screen is a similar Cougar, hit by a much larger bomb, also buried. In both cases, the whole crew survived and were back on duty the next day. The V-hull and the standoff from the ground is the beginning of the answer to why these vehicles work, but it's not the full answer. MRAP vehicles also include other design factors, such as blast mitigating seats and floating floors and crush zones. However, in this talk, we'll look just at the V-hull structure. Assuming an underbody blast, the image on the screen shows two scenarios to illustrate how the V-hull works. With a flat hull, when a pressure wave hits a target, it's reflected straight back again. This results in the vehicle being imparted with high axial vertical momentum. With a V-hull, the internal angle deflects the blast pressure waves more laterally, reducing the axial upwards momentum. The lower the internal angle, the better the V-hull is at deflecting an underbody blast sideways. Additionally, it's stiffer due to its geometry, and so damage to the hull is much reduced. So what's the catch? Low internal V angles also raise the centre of mass of the vehicle, giving it a larger battlefield silhouette. It also affects the vehicle's handling characteristics, such as its manoeuvrability, top speed and vulnerability to roll over, and space for the crew compartments also reduced in a V-hull vehicle. This presentation looks at some attempts to improve on the hull design that keeps the blast-resistant benefits but reduces some of the drawbacks. The single V-hull structure is the baseline design because it most closely resembles the form used in MRAPs. Although the exact design remains a closely guarded secret for obvious reasons, the internal V-hull can be estimated from photographs to be around about 120 degrees. This is also the angle used in prior academic work by Chung et al. In that work, they used 2mm cold form steel plating to produce a 1:8 scale V-shaped hull, based on the earlier Casper South African APC dimensions. They assumed a very tight bend radius of 4mm, but the influence of the actual bend radius wasn't considered. We followed up with this, looking at blast deflection for rigid V-hulls using computational modelling, and we demonstrated the influence of the tip radius and internal angle on axial impulse transfer to the structure. With a constant standoff distance from charge to tip, when you increase the tip radius, you cause a significant increase in the impulse. Increasing the internal angle has a similar effect. Some of the increase is attributed to the change in the clearance height. From the left-hand side, you can see that even though the standoff distance is constant, when you increase the tip radius, you're going to decrease the clearance height. This might be good for vehicle dynamics, but it's not good for blast protection. On the right-hand side, shown for a particular internal angle, when the clearance height is maintained, then the standoff distance has to increase with an increase in tip radius. The increase in tip radius reduced the ability of the structure to deflect the blast wave laterally, but the impulse transfer was much the same, because the increase in standoff distance cancels out this effect. However, the peak force on the tighter tip radius structure was much higher because of the lower standoff. All of this was for rigid structures. In the experiments that follow, I want to show you how the damage to a flexible hull is sustained and what implications that might have on survivability. The single V structure with a 120 degree internal angle is used as the baseline. We looked at two different tip radii, 4 and 32mm, consistent with prior work. We also used a W structure hull, sometimes called a double V, which has two V tips which would be directly beneath the areas where the actual crew seating might be positioned, and could offer improved protection for off-centre blasts. The The central angle alpha offers increased standoff distance in the event of a central underbody blast. The double V or compound V tries to combine the advantage of the small internal angle in lateral blast deflection within the envelope of the 120-degree single V structure. By varying the central internal angle and keeping the base angle the same, the percentage of the width occupied by the sharper angled central V is varied. How do we do this? We perform small-scale blast experiments, where we perform 1 to 8 scale experiments where 50 grams of PE4 can be equivalent to tens of kilograms of TNT. The structure was clamped along two sides in a newly designed black clamp frame that prevented it from interfering with the impulse transfer and deflection mechanisms. Cylinders of PE4 were detonated from the rear at the desired standoff distance from the tip of the structure as shown in the right-hand photograph. For the single V structure with a 32mm radius, we also painted the rear side with a speckle pattern for transient displacement measurements. So what happened? On your screen you can see some photographs of the damage sustained by the single V structures. The ones with the tighter bend radius at the top displayed pinching failures around the work-hardened ridge tip. The displacement along the side ridge was greater than the tip displacement, as you can see in the cross-sectional photograph on the bottom left-hand side. The tip inverted only after the structure ruptured along the side of the ridge at 50 grams. The larger tip radius in the bottom right-hand image shows that there's more localized deformation within the ridge section because of it's less work hardened. There's also less risk of pinching, so the structure in general was less rigid but more ductile in its damage response. On the screen now you can see deflection time histories from some of the tests with the 32mm bend radius single V. It wasn't possible to perform the same experiments using the tighter bend radius because the pinching failure mode would have obscured the speckle pattern on the rear side of the panel. For these images you can see that the initial part of the deflection time history is missing. This is because of motion blur in the first two frames of the high-speed camera footage, making the initial rise in displacement difficult to capture. However, you can see the general characteristics of the transient response, including the peak displacement after approximately a millisecond and the post-peak oscillation response due to the elastic recovery and the elastic vibration of the structure. As might be expected, the higher charge mass produced larger displacements, and you can see that the repeatability is very good, with two 15-gram PE4 detonation experiments shown on the screen. The permanent displacement was approximately 5mm less than the transient peak due to the higher plastic capacity of the structure. In the compound V structures, the tight tip radius made pinching failure around the central ridge a dominant damage feature in these panels. However, the intersection between the base V and the central V shifted the location of maximum deflection away from the ridge section to this outer intersection point, approximately a third of the way along from the centre. This is also the location of the rupture in these designs that didn't maintain their structural integrity. Rupture tended to occur alongside a structural hardpoint. It's an asymmetric response because rupture tends to happen on one side due to a slight imperfection in the material. This then rotates the entire section, but otherwise the deflection profile of the left-hand side of the plates match the 35-gram profile fairly well in the cross-section graph shown in the bottom of your screen. The W structures performed poorly. They exhibited large amounts of tearing along the central bend for a very low charge mass of 8 grams of PE4. Its impulse transfer characteristics couldn't be compared to the other designs due to the premature tearing failures. Increasing the central angle and changing the geometry of the W didn't improve things very much. We were able to see an increase in the rupture threshold to 10 grams. Increasing the clearance height and therefore the standoff distance didn't eliminate this premature rupture mode. This type of failure is attributed to pressure recirculation in the central region. Effectively, the blast is trapped inside the W rather than deflected laterally or reflected vertically. For a W structure to become a viable option, other strengthening and stiffening mechanisms would need to be added to the design to eliminate the potential of trapping of the blast wave and to deal with some of the very flexible response of the structure. But damage is just one aspect. When we look at the impulse transfer from the different designs under the same test conditions, you can see some trends in the graph on your screen. Although many of the impulse values are within 10% of each other, which is just about within likely experimental variation, there is a consistent trend where the single 120V structure outperforms the others, consistently showing lower impulse transfer magnitudes for a given blast test scenario. This is especially true at higher charge masses, where the difference exceeds the experimental variation by some margin. The compound V shapes don't seem to show any dominance of the central V angle in its results, which was surprising. To summarise, there are many possible performance measures for potential MRAP structural design hulls. Displacement of the hull indicates the damage done to the structure by the blast. Introducing a compound V or increasing the bend radius of the V-tip both affected the overall shape of deformation and shifted the location of the peak displacement away from the central ridge. The compound Vs have a lower midpoint deflection but much greater off-center deformation. A very stiff response can be a bad thing if brittle rupture failures ensue at structural hard points. Rupture Thresholds looks at preventing the ingress of the blast wave and the products into the crew compartment. It is essential that the occupants of an MRAP vehicle are not exposed to these. However, the use of an internal double floor might mitigate the seriousness of this problem. The W structure in its current form offers little potential and would need further development to address the blast pressure trapping and increase its rupture resistance. Impulse transfer is an important factor preventing global movement of the vehicle and its crew, thereby reducing injuries from acceleration or impact with items in the cab. The single V hull structure offers slight advantage on those grounds. So in short, we have yet to improve upon the single V structure for vehicles likely to experience underbody blasts. The usual comment that vehicle design is more than just blast protection and structural response also applies, as finding here do not address the important challenges of vehicle mobility or its repairability after a blast event occurs. With that, I'll finish by saying thank you for listening to me. If you liked what you heard, you can read more about my work in some of the articles on the screen, or you can contact me at the University of Sheffield on the email address or Twitter handle shown. Once again, thank you very much for your kind attention.